Okay, so back to kinetics. Yesterday when we stopped, we were talking about mechanisms. And when we find the rate law, what's the rate law? Rate is equal to what?
A bracket, power thing. Order. Got it.
And A and B are what part of our equation? They're reactants. And it's raised to the power of the coefficient. And how do we write the rate law? Where does the rate law, what is it written from? The rate, the slowest or the rate determining step. Okay, so that's just a refresher. That's how we can write the rate law. Today we're going to look at the method of initial rate. So we're looking at the rates immediately as they start, and somebody's in the lab doing all these manipulations and taking and recording this information. And we're going to write the rate law based on the information that they collected within the lab. Okay? Everybody, are you good, Lauren? Okay, so here we go. So here is our equation. This is the Cliff Notes. So we cannot write the rate law from that equation because we don't know anything about it, whether it's an elementary one step or where the slow step is. We don't know the whole mechanism. But this is data that they recorded in the lab, and we're going to write the rate law. We're going to determine the order from this information. So what happens is they go in the lab and they keep something constant. They're very methodic about it. Something is kept constant so they can see what's going on. So we're going to use the ugly algebra way. I'm going to show you ugly algebra, and then I'm going to show you the nice clean way. You can do it either way. Either way is right. It just depends on your preference. So the first thing I'm going to do is I'm going to look at all three of these experiments, and I'm going to look at one that something is held constant. So let's look at experiment 1 and 2. So what is held constant in there? And if you're looking at fluorine, in real life, 0.0318 and 0.0315 is constant. Okay, constant's never really constant. So this is held constant. So what I'm going to do, I am going to look at what order is NO2. So first thing you're going to do is write a skeleton rate law. So skeleton of our equation. So rate is equal to NO2 raised to the power of something. We don't know what it's raised to. F2. Hold on, let me go erase that so I can write it better. So NO2 raised to the power of something. We don't know what it's raised to. And then we have F2 raised to the power of Y. We don't know what F2 is raised to the power of. We don't know those orders, and we're going to figure it out. So there's our skeleton. That's our backbone we're going to work off of. So what we want to do is we're going to compare two of the experiments. We're going to look at it and compare, make sure one thing is held constant. So the very first experiment I'm looking at I'm going to look at experiment 1 and 2. And we are going to divide them and come up and solve for X on NO2. So it doesn't matter which one you put on top. I like easy math, so I'm going to put the bigger number on top. So that means we are going to compare 1 over 2. So you're going to go and write the rate law for experiment 1. So we know the rate, 1.9 times 10 to the minus 3 is equal to K, we don't know what K is, times the concentration of NO2, which is 0.0482 molar, to the X power, times the concentration of F2, which is 0.0318 molar, to the Y power. I am going to put that all over 2, the rate law for 2, experiment 2. So that's going to be 4.69 times 10 to the minus 4 is equal to K to the 0.0120 molar to the X power over times 0.0315 molar to the Y power. Now I want to solve. Before I solve this, I'm going to cross out things that are the same on top and bottom. Not the X's. We are solving for X.
So we also get rid of the Y?
The Y is out too, yes. Okay, so put that in the calculator. 1.9 times 10 to the minus 3 divided by 4.69 times 10 to the minus 4. $4.05? All right, and that is equal to, now divide 0.0482 divided by 0.0120. 4.01 to the X power. So what is X? 1. X is 1. So what you need to write, that is not good enough for the AP exam. You cannot just say X is 1. What you have to say is that this is first order with respect to NO2. If you just say X equals 1, they're not going to give you your point. Everybody good with that? Okay, so let's look at F2. So we're going to look at F2 and look at where NO2 is held constant, which is 1 and 3. So easy math, we want to put the bigger numbers on top. So that means we are putting 3 on top. So 3 over 1 this time. Three over 1. So this time it is going to be 7.57 times 10 to the minus third is equal to K times the concentration of 0.0480 to the first order times F2, which is 1.127 to the Y. Put that all over 1. And then we get 1.9 times 10 to the minus 3 is equal to K over 0.0482 to the first power times 0.0318 y. Again, go in and cross out everything that's common, K, and then we have the NO2. And then do your division. So 7.57 divided by 1.9, 3.98. And we're going to set that equal to 0.127 divided by 0.0318, 3.99. And that is to the y power. So what is y? 1. So this is, again, you've got to write first order with respect to F2. Okay, ugly algebra way. If you like math, there you go. Any questions on that?
So first order with respect to F2 is that order of F2 as well.
Yes. Let's go to the next question. It says, determine the overall order of the reaction. So it says determine. When they say determine, they are telling you calculate. They're not saying what is the order. They're saying calculate it. So they want to see it. 1 plus 1 equals 2. So this is second order overall. Write the specific rate law for the reaction. So now we can write the rate. So rate is equal to K times the concentration of NO2 to the first power times F2, concentration of F2 to the first power. And do you have to put those ones there? No. Either way is fine. Questions on that? Now they have told you to determine the rate constant. And it says include units. If it tells you to include units and you don't, they are very, very big in kinetics and the units in kinetics. And if you don't include the units, you won't get the point if they ask for it. So if you go back to our data on the last page, you see that we have 3 data points, 3 experiments. You can use any of those experiments to solve for K. But I will tell you that the AP readers use the very first experiment when they are doing their rubric. So I would use the first one every time. So go back to your data and let's plug in. Rate is 1.90 times 10 to the minus third is equal to K, that's what we're looking for, times the concentrate, I'm going to go back real quick. I'm going to put the units for our rate, so that's molarity over seconds, is equal to K times the concentration, 0.0482 molarity to the first power times the concentration, 0.0318 molarity to the first power. So put that in the calculator and solve for K for me. 1.24. So K is 1.24. The units. So let's take a look here. If we have m over seconds, and then we divide by m squared, so this looks like this, m, right? The m's go away. So we are left with 1 over second m. So 1 over second m.
So what's the unit?
That is the unit.
No. What's 1?
1.
How do you get second M?
How do I get what? You will see it also written as 1.24 second negative 1 m negative 1. Okay, so I told you this is a unit where they are really big on the units. They will test you on the units. So how can you determine the units without doing the math and making sure that they're there? So here's your shortcut method. So what you're going to do is, what you're going to have here is 1 over your time, whatever your time is, minute, seconds, whatever. And then you're going to have molarity. And then what you need to do is you need to look at your overall order minus 1. So that is time, big M, and then your overall order minus 1. So if our overall order was 2, then our unit is going to be 1 over T, big M, 2 minus 1, which ends up giving us 1 over time, M, and that's it. 2 minus 1 is 1. Okay? You'll see multiple choices out there. What order is this unit go to? Okay, let's do the table logic. Looking at table logic, not using ugly algebra. So what we're going to do here is I'm going to look at this table, and I'm going to do some comparisons here. So what I'm going to do is, again, this is experimental data that has been found. One thing you will notice is these are pressures. So when we start writing the rate order, we do not write brackets. That is for molarity. For pressure, it is going to be P subscript whatever your compound or element is in brackets. So they are really big on not in brackets, sorry, close parentheses. In parentheses on pressure. So table logic. So find one that's constant. So let's take a look at, somebody pick one. Which ones do you want to look at? NO or H2 first? NO. You want to find the order for NO first. So we need to find the experimental data where NO is changed, but H2 is held constant. 3 and 4. So let's go ahead and cross out H2 right now. So what I want to do is I want to know, so as I go from 3 to 4, what happens to our pressure? It does what? How much? By how much? It doubles. So it goes up by 2. So I want to find out what that number next to that superscript or that exponent next to that number is. So let's look at the rate. As I go from 3 to 4, what happens to my rate? It quadruples. So it goes up 4. So what does that exponent have to be to get me a quadruple rate? 2. So what order is P and O? 2. So P and O is second order. You use table logic, you cannot stop right here. You've got to have some justification. So what you can have to write is P and O is second order as the pressure of H2 is held constant the pressure of NO is doubled. Which results in the initial rate quadrupling. Therefore, second order in respect to P&O. Okay, so that's where you have to decide. Would you rather do the math setup, or would you rather write a sentence? So now we have P and O. Now let's look at H2. So we have to pick an experiment where NO is held constant and H2 changes. And that would be 1 and 2. So what happens as I go from 1 to 2? What happens to the pressure of H2? It doubles. When that happens, what happens to the initial rate? It doubles. So what does that exponent have to be? A 1. So this is first order in respect to pH2, the pressure of H2, as the pressure of NO is held constant, the pressure of H2 is doubled resulting in the initial rate doubling. Therefore, first order. Okay? So choose whichever way you want to do it. Which way do y'all like? Which one's better?
The tip is better, but like, does it really work when the numbers are pretty?
Yeah. Numbers are usually, they're usually going to look very similar. So,
Okay.
it's not going to be all like an exact 2, but it'll be close.
Well, yeah, but like, I feel like sometimes it would be a lot harder to...
Well, let's go on to the next one, or overall order. Determine overall order. So we have 2 plus 1, which means our overall order is 3. So third order overall. Write the specific rate law. So rate is equal to K. So here you go, no brackets, parentheses, big P, subscript NO, close your parentheses and square it, because we're second order, and do the same for H2 to the first order. What was that? 1.03. Where'd you get 1.03? Oh, for the last one? Okay, so now the last one says determine the rate constant. Again, remember, go to that first one to determine your rate constant. So 0.66 is equal to K. And if you see this right here and they haven't asked you to determine the rate constant yet, you don't have to substitute K in there. You can just write K because they haven't asked you to solve. And then we have 400 squared times 150, and solve for K for me.
Wait, do we have to put the units of millimeters or whatever that?
I didn't put it in there because I want to do the shortcut at the end.
Okay.
What did y'all get?
Lots of zeros. It's 2.8 at
2.8?
yeah, it's like 2.75 times 10 to the
2.75 times 10 to the negative 8. Okay, so let's look at our units. It's going to be 1. What's our time? Go back, and our time is seconds. And our unit is millimeters of mercury this time. Our overall order is what? So 3 minus 1 is 2. So this is going to be millimeters of mercury squared. Everybody good?
Sorry, guys.
Mr. Popular over here.
Yeah.
Okay, so this is a nice, pretty one. I'm just kidding. There's 3 in here. We're not going to look at I just put this in here for you to look at. Now somebody else is popular. I don't expect them to put anything like this on the AP exam, but this is a little practice if you want to challenge yourself.
I keep getting a call from a random.
From Colleen.
Yeah, answer it. Every day in this class, I get a random call from a different.
I should have answered it.
I would have said something last week, but to be honest.
Hello, this is Miss White.
Okay, so again, this is just something for you to challenge yourself if you want to take a look at that, but I'm not going to do it, and I don't foresee that being on the AP exam. So last thing, rate law, and this is looking at instantaneous rate. So this is looking at the concentration over time. So you can see as time goes by, that what happens to that slope as we go. So what you can do is you can take an instantaneous rate. So find a time, say 8, right here. And then you can get the concentration. So y over m, or y over x is what? Slope. We can get our slope. What you do is you take this draw a tangent to that line, tangent to that point. And you can find out what that instantaneous rate is at that point. And you could do this for each time and go through and find those rates. But this is for those calculus people that like that. That's not going to be something that's on
No one
the
likes
AP. Nobody likes it.
Nobody likes
No.
derivatives.
No derivatives? You don't want to do the derivative? Okay, so this was just something there to throw out there, show that to you, and that will conclude the lecture. Homework is 2B or 3B.
Marcus, do derivatives.